course of just as things go on. Okay, Edwin, are you there?
Yes. Are you ready?
Yep.
Everybody
Yes.
ready? All right. So let's get started. Yeah. I'm streaming now, and yeah, to echo what everybody says, I don't think it's helpful if I spend like an hour walking through my thought process and coding everything line by line. In the sense of explaining every single intricate detail, because obviously this is something that it's not a spectator sport. It's something that you have to do by yourself, and the way I implement it is not always going to be the best way, and also the way I implement it is it also I already did this problem like an hour ago, so there are certain like challenges that you didn't see me go through, and it seems like I've contrived everything out of my head, but that's certainly not the case. So that's why it's not very an effective medium for me to spend in essence trying to go through every single little detail, and you really have to do it yourself, and then you'll understand the choices I've made, and also why certain things pop up frequently and why certain things don't pop up as frequently. But yeah, in the interest of time, I definitely don't want to impede the discussion too long, so I'll only take 15 minutes for this problem. And hopefully you've taken a look at this problem. It's a very famous problem. I understand everybody wants to have more practice with dynamic programming. And this is a great classic dynamic programming question called n queens. And this question asks, given n queens, or say 4 or 5 or 8 or 9 queens on a 4x4 chessboard, so let's say it's 4 queens on a 4x4 chessboard, how do we place these 4 queens on this 4x4 chessboard so that no 2 queens attack each other? So if you're familiar with chess, you understand a queen can go anywhere. They can go row-wise, column-wise, and also, of course, diagonally. And you can see in this example, what we have is we have 8 queens on an 8x8 chessboard, and you can see that each queen is not able to attack each other. So our task is to devise a board just like this. Just given the number 8 as our input, or 4 for a 4x4 board, or 5 for a 5x5 board. And you can see here in this example, given an input of 4, you have a 4x4 board, and you can see this mock chessboard where a Q stands for queen and a dot stands for empty tile. And you can see there's 2 possible solutions, 2 distinct solutions where we can place these 4 queens on a 4x4 board so that none of these queens are attacking each other. So in terms of dynamic programming, as we really talked about like ad nauseum, you really have to think in terms of combinations and trying out as many different combinations as possible in such a way that it will give you a complete solution to the problem that you're looking for. And when it comes to building out these combinations, it's always helpful to start out small. So let's say, for example, in a 2x2 board, can we place 2 queens on such a board that they won't attack each other? So let's say that there's a 2x2 board, and then we place a queen here, and we place a queen here. That looks like it may be right, but remember that queens can't be diagonal from each other as well. So in our solution, we have to, in essence, we have to make sure that we have to check that queens are not in the same column, and queens are not in the same rows in terms of being able to attack each other, but also in terms of diagonal, that they're not being able to attack each other. And given this example, we can see that a 2x2, given an input of 2 queens on a 2x2 board, we're going to have to return no solutions. However, for a 3x3 board, can we actually have a possible solution for this? So when I always think about dynamic programming, always start small, and then we can always build our way up. Well, let's assume that I put a queen here, and I put a queen here. This seems to be legal so far. So I put 2 queens so far. Can I put a queen in the 3rd position that allows us to not attack the other 2? So that's the question we have to answer for a 3x3 board. But you can see how this pattern is growing and how we're thinking about ways of trying to in essence, try to find out what is the recursive solution that of all the combinations that we have to try. We have to make sure that when we place a queen on the first row, we try a queen can be placed on any position on the first row, and then when we go on to the next row, we have to make sure that whichever position that we put the queen on the first row, we have to try out every single combination of every single queen in the first row against all possible combinations of queens on the second row and all possible combinations of queens in the third row. So hopefully that makes sense. But you can see how this has become a real iterative problem. And because we're calling the problem itself, we can also turn this iterative problem into a very intuitive recursive solution. But of course, every single recursive problem can be implemented iteratively. But I think let's do a recursive implementation since they're more intuitive, I found, and also they're more fun to do. And I think everybody needs more practice with recursion. So, given the solutions, it seems like the output is a list of strings. So what we expect is our solutions expects there to be a list, and we have to return a list of possible solutions. But then each solution itself is a list. So how do we get started with this? So because we're thinking of doing a recursive solution, and we're thinking of, in essence, traversing every single row in order, this is actually a depth first search problem because it's recursive and we're going through every single, let's say, we're going through every single row and trying out every single combination in order, and we're incrementing, and after we're done with the first row in terms of all its combinations, we're going to try out the second row to see all the possible permutations with a first row. So given that, we're going to call this, we're going to implement a depth first search problem. And here's the kicker too, in terms of, we don't actually have to implement the full matrix as well, because as we know, we can't put a queen, you can't have two queens on the same row, right? So the only difference is in when constructing this board is, all we have to know is that we only care about the columns, really. We can actually put everything in one list because queens can't be put in the same row. So we only care about a list of possible positions of queens where, let's say this is one, oops, I think I accidentally refreshed here. But let's say we put a queen of position here, 5 and 7, or let's do 3, and so on and so forth. So we can actually represent the chessboard as one single list where a queen will be placed in column 1 in the first row, and then in the second row it would be placed on column 5, and then in the third row it would be placed on column 7. So we're actually having the index position double as the row number. So that's a very neat trick, so that we don't have to construct the full matrix in order, because we know that each queen has to be, as you can see in this image here, each queen has to be in their own independent rows. So we only care about placing queens on the right column, if that makes sense. So our task is, given our board, we know we have to place each queen on each of their own rows, but we have to make sure that the column that we place this queen in does not conflict, as you can see in this 2x2 example, does not have a diagonal position with a previous queen, and also, of course, is not in the same column as the previous queen, as any other previous queen that we place on the board so far. So we're going to construct a mock list of the column positions. So given, let's say, a 4x4 example, this list will only be 4 columns, and then that will be our board, so to speak. And then of course we're going to start in row 0, the first row, and then we're going to have we're going to build the path for every single combination. So when we're trying out one combination of one possible solution, we're going to be adding on to this as a possible solution. And of course, we're going to, if we find a valid solution, we're going to add it to our list of solutions so that we can return all of our solutions, as you can see here in this expected output at the end. So let's unpack, essentially, let's define this depth first search. And depth first search, I mean, it may be confusing because this is essentially a graph kind of problem, but it's also a very simplified kind of graph problem. So if you wanted to call this like place queen, or call this function like place the next queen, I think that would actually make more intuitive sense. But you'll see, but I think it's useful to call it depth first search for now, because what we always expect is that patterns always tend to crop up, and when you do enough of these problems, you can see that depth first search comes up in a lot of problems, in graph problems, in dynamic programming problems, and so on and so forth. And you can actually implement this fairly quickly once you have enough practice with it. So we're going to call this solution from bar, and then we're going to call this solution. So let's implement this. So if our row, right now we start at row 0 in terms of all our first combinations, and then we're going to check if this is equal to the length of column. And if this is equal to the length of columns, then we've hit the end of the board. So if the row number, once is in our recursive implementation, if we first start at 0, and then of course in recursion we always go to the next part, that's a smaller subset of the original problem. We're going to go to row 1, then row 2, and then once we hit at the end, when row is equal to the length of columns, when in the 4x4 board, when n is equal to 4 and row is equal to 4, and it's equal to length of 4 columns, we're going to hit the end. And if there's been no errors or no return falses, we're going to know that we have a valid solution. And we're going to append our solution so far to our solutions list that we can return at the very end. Okay, so that takes care of the base case. So now, in terms of the actual recursive step, what we're doing now is we're going to loop through every single column in the columns so far. So let's just try for 4x4 examples, since we already have this, we already are given solutions for them. So let's just start with the input of n equals 4 on a 4x4 board. So for each column, for column 0, column 1, column 2, and column 3, for what we want to do is, as explained before, we want to make sure that given the current row position that we're on in row 0, the index position doubles as the row number. So we know that we're going to place the column in this row index position of 0, and we're going to place this column let's say we start out with column 0, we're going to place the column 0 in the row position 0, and that would essentially be our first solution. So the queen will be placed on position 0, or the first position. And then we're going to keep on going back forth. And this essentially means that we're placing the queen on the right position on the certain column. But now we need to check to see if it's actually valid so far what we've gotten. So we're going to make another function we're going to call it check valid, and we're going to pass it the columns that we have so far and the row that we care about. And we're going to write this function later, but we're just going to stub it out. So of course, if it's valid in terms of the current combination that we're on, the current path traversal that we're on, we're going to make a new row, and we're going to, so LeetCode expects us to make, every time we make a new row, we have to make a string of periods. So we're going to have to do the length of columns on a 4x4, so we have to make the dot 4 times. And then after we construct this new row, we're going to do another depth first search, of course, with the same columns that we have, with queens pre-appended on previous rows that we've already traversed. And then, of course, in a recursive solution, we always want to go on to the next row, the smaller subset of the universal problem we're working on. And then the solution so far, we're going to append this new row that we've created that stops at the column that we've decided that is a valid placement for the queen, and then we're going to place the queen here, and then place the new row here, and then the column. We have to make sure we're not putting on the same position as the queen, as the Q, and then we're going to end it there. And that is our solution so far in terms of what we expect. And then we're going to, of course, pass on the solutions that we built so far in the depth first search. So this is what the solution looks like in terms of, seems like we've done, I did a lot of, it seems like they're considering this as one line, which it should be, but this is gone too big, so let me minimize. Okay, so now it looks better. Okay. All right, so now let's actually check to see if we can place the queen on that valid position. Okay, these indentations, okay. So let's actually define the check valid portion, and this is really the heart of the problem. I guess the depth first search is, that insight is very important, but we're going to check to see if whether we can place the queen on that certain column. So if we can actually place that queen on that row, on that particular row, and then in terms of checking whether it's valid, we want to loop through, I'm going to call this inner row, and for every single row, and then we're going to check if this queen that we're going to place on this row that we're on is on the same column. Check if this queen is on same column as previous queens, right? And we do if columns. We're going to check every single inner row of all the rows we have so far. If that is equal to columns of our current row position, then we're going to return false. It means this is not a valid position, and we have to return false for this particular combination. So we have to try the next rows in the next columns. Okay, so we also have to check the diagonals, if you remember. So we have to check diagonal. And we don't have to check rows again because we're doing everything off of one list. So we already made the key insight that each index position which we've assigned to be the row position, each queen is going to be in their own row. But we, of course, have to check diagonal, that queens are not placed on the same diagonal. And the mathematical trick for here is that if the column distance is equal to the row distance, we know that the two queens are on essentially the same square, and they share the same vertex, and that means they're on the same diagonal. So let's actually implement that. So the column distance is equal to the absolute value of the columns we have so far for the inner row minus the columns on the row we're currently on. And then the row distance is equal to the row minus the inner row. We don't have to do the absolute value here because remember, we're looping through every inner row to be the row. So row is always going to be greater than the inner row. So we don't have to worry about absolute value there. And then if the column distance is equal to the row distance, we know that we're on a diagonal, and this is an invalid position that we have to return false. If it passes these two checks, then I'm not sure. Okay, so if it passes these two checks, then we can return true. Okay. All right. So that's essentially what the problem is asking about. So we're going to do a depth first search starting at row 0, and if we're able to hit at the end that the row is equal to the length of columns, we have a valid solution, and we're going to append it to our solutions list and return it. And while we're trying out every single combination, we're going to loop through every single possible column, and we're going to assign, in this particular position, the column that we want, that the queen should be, of course, like placed on, like, say, on a 4x4 example, they can be placed on the first, second, third, or fourth column in each of the rows. And if this is a valid position, then we're going to add it to, we're going to add the 3 dots in the queue into our solution so far, and we're going to keep building up that solution. And if it's valid all the way and doesn't return false at all, then you know that this is a valid solution that we can append, and then we can try out the next possible solutions if they exist. So this is what the problem looks like. I'm going to try running the code, and hopefully there isn't invalid syntax solution so far. I think I just probably missed here. I wonder what probably is like a list, a new column row. Oh yeah, this is a rookie error. We're going to add the column here, and then we're going to slice it there, and then hopefully that will work. But yeah, if there's any questions, this is what the answer looks like.
So I thought this was super interesting, and the particular part that I think is why I think it's really interesting is where you decided that you can basically say that define it as a row of numbers where each the index of the row represents the column, and the value in the row represents the row, or vice versa. Because originally when I saw this problem, I was like, okay, how would I solve it? I'm trying to think in my head, and I actually didn't get to that conclusion. But I think that's like one of the more powerful conclusions. More so, if this problem was like, how do you place 8 rooks, or how do you place n rooks? At that point, you've already solved the problem. You've basically created another problem that is an equivalent of the problem you're discussing, but has like a limited amount of space. And I think that kind of touches on like the mathematical side of computer science, or of like solving these problems, where if we're essentially mapping one problem to another problem, and we can solve this other problem, then we can solve our original problem in a very simple way.
Yeah. Yeah, it's this problem, like, it's a hard problem in LeetCode for a reason, and it's a very classic problem because, let me give it a like too. It's because not only are you have to juggle the recursive depth first search, and so, you're trying out every single combination in turn, but you have to check inside your traversal. You have to check whether each position is valid. Whether the current position that you're trying to place the queen on, is that a valid row? Is that are you making sure that this queen is not on the same column as prior queens, and doesn't share the same diagonal as prior queens? So that's why this problem is so that's why I would recommend, if you're still not really grasping this, I would recommend doing medium or easy problems where you just care about the depth first search, and you don't have to check whether each position that you're placing the new element on, whether that is a valid position or not. And so the only thing you're juggling right now is the depth first search. And the reason why this is a hard problem is because not only do you have to juggle this portion, but you also have to juggle the validity check.
Yeah, that makes sense.
But yeah, like if this is new to you, like depth first search is a common pattern that repeats itself. So once you get familiar with the depth first search, you'll see that we're just really you will see a lot of graph problems and dynamic program problems are just extensions. Like this problem is just an extension of the depth first search problem because we're not going through a matrix, but we're going through a list and we're doing the check valid. But besides those two things, it's really this is a really classic pattern that you'll see repeated over and over again. And the reason why we did this recursively instead of iteratively is because you could have done this iteratively. You could have just made a stack, and you could have just looped through the stack and keep pushing on to the stack and check every single combination that way. But this is a lot more. Once you get used to it, a very intuitive solution because you don't have to worry so much about trying out every single combination and holding it in your head. You're letting the computer take care of the details for you because when you say just let me do a depth first search and let me recursively do it a depth first search again, uh, I'm trying out depth first search for every single column. So you're abstracting away that implementation detail of checking every single possible combination to the computer. You're just saying, yeah, for every column, I want to do a depth first search on the next row. So you can see how the computer is going to try out every single possible permutation for you.
So I think that's also another good point where like this problem can actually be solved by literally coming up with every single way to place 8 queens on a chessboard and then doing a validity check on all of them. But you set up the problem in such a way such that you don't have to do horizontal and column checks by simply setting up your problem in the right way, and then all you have to do is check for the diagonal. And I think that's super interesting.
Yeah, well, you have to check. You have to check if the same if it's because we're placing the queen on the next row. I mean, so every single index position as we're looping through uh, the columns, we just have to check it to see if this queen is going to be on the same column as prior queens, and then of course checking the diagonal. But so we have to do these 2 checks here. But yeah, we don't have to do the check row here because of the way we set up the problem.
Interesting.
Yeah. But yeah, that's it for me. If there's no other questions.